You have developed your TLC plate. The solvent front is marked. Now you hold it under the UV lamp and see nothing. So you reach for K-4, but is K-4 actually the right stain for what you are looking for? Most chemists reach for the same one or two stains out of the habit, but every stain has a specific chemistry behind it, and choosing the wrong one means you are looking at your compound through the wrong lens. We will talk about 5 stains: UV, iodine, ninhydrin, K-4 and CAM, and we'll talk about which one to reach for and why, and what the chemistry behind each one is doing to your compound. UV is always your first step, and it is one of the non-destructive visualization method. You can UV visualize a plate, mark your spots, and still use a chemical stain after that. That makes it uniquely valuable. At 254 nanometers, this is what most labs use. The plate itself fluoresces green under the lamp. Compounds that absorb at this wavelength, like aromatic rings, conjugated pi systems, most heterocyclics, block that fluorescence and you see a dark spot where the compound is. So you are not seeing the compound directly, you are seeing where the compound is blocking the plate's fluorescence. At 365 nanometers, there is a different phenomena. Some compounds don't just absorb UV, they absorb it and emit visible light at a longer wavelength. This is fluorescence, and certain natural compounds, fluorescent dyes and compounds with extended conjugation will glow visibly under 365 nanometer light. These appear as a bright colored spots, not the dark ones. What UV cannot detect are saturated compounds, simple alcohols, aliphatic chains, most carbohydrates. Anything without a UV chromophore is invisible under UV. If you hold a plate of glucose under UV, you will see nothing. That is not a failed plate, that is a compound that needs a different chemical stain. Iodine is the simplest staining method. Put your plate in a jar with iodine crystals, close the lid, wait 30 to 60 seconds, and yellow-brown spots appear where your compounds are. Take the plate out, mark your spots immediately, because here's the key thing about iodine: it is a reversible reaction. Why is it a reversible reaction? Iodine doesn't react covalently to your compound, it forms what is called a charge transfer complex. The iodine molecule accepts electron density from pi bonds in your compound, creating a colored interaction. But when the iodine evaporates, the complex breaks and your compound remains same. This is why iodine is generally non-destructive. So what iodine detects? Anything with pi bonds like alkenes, alkynes, aromatic compounds or carbonyl groups, and what it misses are saturated compounds with no pi system. Alcohols, alkanes, simple amines are often invisible or very faint. There are practical limitations that iodine gives you a yes or no answer. All spots stain roughly the same yellow-brown regardless of functional group. If you need to distinguish between two different compounds with same functional group on the same plate, iodine will not help you. That is when you need a more selective stain. Ninhydrin is your most selective stain. It reacts specifically with primary amines to give an intense purple color. If you are working with amino acids, peptides or any compounds with a free primary amine, ninhydrin is your go-to molecule. The ninhydrin chemistry is also worth understanding. Ninhydrin reacts with primary amine through a condensation reaction. The amine group attacks the ninhydrin carbonyl group, releasing carbon dioxide and an aldehyde from amino acid side chain. The resulting intermediate then reacts with a second molecule of ninhydrin to form a deeply colored purple product. It is a two-step reaction that is essentially irreversible. Beside primary amines, secondary amines can also give a but different color under ninhydrin. Instead of purple, they give an orange to brown color. This is because the secondary amines cannot release the aldehyde intermediate the same way, and the mechanism follows a different pathway with secondary amines. So ninhydrin lets to distinguish between primary and secondary amines on the same plate. In lab, always heat the plate after applying ninhydrin. Room temperature development is slow and incomplete. Heating the plate gives you a sharp and intense spots. Ninhydrin staining is destructive, so once you heat the plate, the compound is chemically altered. KMnO4 or potassium permanganate is the most universal stain in synthetic organic chemistry. It oxidizes almost any functional group that can be oxidized, which makes it your broadest spectrum staining option after UV. The staining solution is typically prepared as KMnO4 in potassium carbonate and water. The permanganate ion is a powerful oxidant that reacts with electron-rich functional groups like alkenes, alkynes, alcohols, aldehydes, and many other groups. The manganese reduces from +7 to +4 oxidation state, forming manganese dioxide, which is the brown insoluble product you see on the plate. The color of the spot tells you about the ease of the oxidation. Easily oxidized compounds like alkenes, alkynes, aldehydes give immediate dark brown spot. Harder to oxidize compounds like secondary alcohols, saturated ethers give lighter yellow or pale spots, especially before heating. If you heat the plate and spots go from yellow to brown, your compounds are oxidizing slowly. That tells you something about their reactivity. What KMnO4 struggles with is highly non-polar saturated compounds like simple alkanes and some ethers that have no easily oxidizable site. Also, very hindered functional groups may stain poorly, and KMnO4 is not a selective technique. Everything oxidizable can be oxidized, which means on a complex mixture you get a plate covered in brown spots with little differentiation. Always make KMnO4 solution fresh or use the one that is made within a week. Or solution partially decomposes and gives weaker inconsistent staining. Standard way of making KMnO4 solution is 1.5 grams of KMnO4, 10 grams of potassium carbonate, 1.25 ml of 10% sodium hydroxide solution, 200 ml of water, and keep it in a brown bottle away from light. CAM or steric ammonium molybdate is the stain that separates different compounds by showing different colors. CAM solution contains three active components: cerium sulfate, ammonium molybdate, and concentrated sulfuric acid in water. This is not a single oxidant like KMnO4, it is a dual oxidant system. The molybdate ion and the cerium ion work together and the sulfuric acid provides a strongly acidic environment that activates the oxidation. The reason CAM gives different colors for different functional groups, which is the key insight here, is that cerium and molybdenum form different colored complexes depending on what they are oxidizing. Alcohols give blue spots, ketones and aldehydes give green to blue spots, steroids and terpenoids give characteristic bluish greenish colors. Sugar gives brown spots. This color differentiation is something KMnO4 simply cannot do. This is why KM is the workhorse of total synthesis and natural product labs. When you are working with complex molecules that have multiple functional groups, like in steroids, alkaloids, terpenoids, KM tells you which spot is which based on color. KMnO4 would just give you a plate full of brown colors. Always heat the plate after dipping in cam. By heating, the colors develop over 10 to 20 seconds and continue to intensify. Be careful because overheating turns everything brown and you lose the color differentiation that makes cam useful. When to choose cam over CMnO4? Complex mixtures where you need to distinguish compound types, natural products, and steroid chemistry, or any situation where the color differentiation matters, you can use cam over CMnO4. Whereas CMnO4 is better for simple reaction monitoring where you just need to confirm a spot is there and when you need a faster result. The decision logic in one sentence is that UV first always. It is a free and non-destructive technique. Then ask, is there any amine present? Use Ninhydrin. Complex mixtures needing color differentiation? Use CAM. Simple monitoring of an oxidizable compound? Use CMnO4. Something with pi bonds and you need reversible? Iodine. Every stain has a specific job and reach for the right one. The next video is about melting point and optical rotation. You have now monitored your reaction with TLC and visualized your spots correctly. But how do you actually confirm your compound is pure and that you made what you think you made? That is what we cover next.